Hello and welcome to this revision session for AQA A-Level Physics in the topic of waves, in particular progressive and stationary waves. So in today's revision session we're going to be looking at the following parts of the specification. We're going to be looking at 3.3.1.1 progressive waves, we're going to be looking at 3.3.1.2 longitudinal and transverse waves, and we're going to be looking at 3.3.1.3 the principle of superposition of waves and the formation of stationary waves. So let's start off by looking at progressive waves. So wave behaviour is common in both natural and man-made systems. Now waves will carry energy from one place to another and can also carry information. Now progressive waves do this without transferring matter with the energy. So a wave which will transfer energy but not transfer matter is called a progressive wave. Now we can consider waves to have the following shape. Now this is an approximation of how waves look. It is extremely simplified. Now it's important to note that you can use waves in many different real-world applications, such as a mobile phone or listen to the radio. Now designing comfortable and safe structures like bridges, houses, music performance halls require an understanding of mechanical waves, whilst modern technologies such as imaging, communication systems show how we can make the most of electromagnetic waves. Now we do consider one entire wave to be when the oscillation of the structure repeats itself once. But what is the definition of a wave and what are the different types of waves? So as mentioned before, a progressive wave is a mechanism that transfers energy and or information from one place to another without the net movement of matter. So you'll notice that in this situation energy is travelling in a particular direction, but the particles do not travel with them during this. Instead, the particles will oscillate or vibrate backwards and forwards, but throughout our wave motion there is no net movement of the particles. So when the particles oscillate in the wave, they will transfer energy between each other, allowing energy to be transferred through the wave. So in a progressive wave, energy is transferred but matter is not, and this is shown in a number of different examples. So for example, when a twig is dropped into a calm pool of water, ripples will form on the water surface. Now the ripples don't carry the twig or water away with them. If you strum a guitar string and create sound waves, the sound waves don't carry the air away from the guitar and create a vacuum. Likewise, when you speak, your voice box vibrates, making sound waves that travel through the air, but the air itself does not travel away from the throat, otherwise you would create a vacuum inside your throat. Now, as we mentioned before, a progressive wave will transfer this energy or information without the movement of matter overall. So instead, the wave causes the particles of your material to move backwards and forwards, as shown in this particular situation. And it could be in different orientations as well, as shown here. Now, we call this movement backwards and forwards as an oscillation or a vibration. So it is okay to say that a wave causes particles to oscillate or vibrate. Now one complete wave or oscillation is when the particles move one way then the other and go back to where they start. So this is a cycle which shows one complete oscillation of a wave. It goes one way, then it goes back to equilibrium, then it goes the other way, and then it finishes back in equilibrium again. Now we say that as this wave will cause your particles to oscillate, the energy will transfer through the wave or will propagate. Now the way in which the particles will vibrate allows you to classify the waves, and what vibrates in the waves allows you to classify the wave. Now just to clarify, a wave is a pathway for energy to move position in the universe, so it can cause energy to change store. Now in a system, energy can change store without the need for a wave, and when this happens, this is called doing work. So for example, we would say that work is done if an energy store changes type without using a wave, so we can say that we've got mechanical work. Because remember, in a system there are 4 ways to change the energy store of objects. You can have work done by a force, work done by an electrical current, heating by waves, or radiation by waves. Now It's important to also note that in the wave the particles will oscillate about a position, but they won't move position overall. Now, waves can be classified as either mechanical or electromagnetic waves and transverse or longitudinal waves. So here we've got our representation of a wave, which is the oscillation of the energy found in the wave. Now, the greater the energy in the wave, the larger the oscillation, and there are two different materials which can be oscillated by a wave, which gives us two different types of wave, or two categories of wave: electromagnetic waves and mechanical waves. So a mechanical wave is a wave which has oscillations of matter, so atoms. So a mechanical wave is caused by particles vibrating at a source, and it will cause the particles to oscillate backwards and forwards. But please remember, there's no net displacement of the particles. The particles are moving back and forth. So we state overall that there's no overall movement of the particles, or rather in fact they're just vibrating backwards and forwards, backwards and forwards. Now, in a sound wave, the particles do not travel from the object making the sound to the object detecting the sound, but the sound wave is a series of particles vibrating backwards and forwards, colliding with the next particle and making that particle vibrate, passing the energy on. Now, particles oscillate or vibrate in a substance and then pass energy on to the neighbouring particles. So that's very important to work through. This is because it means that mechanical waves need particles for energy to be transferred, so mechanical waves cannot travel in a vacuum. Now, an electromagnetic wave is a wave which has oscillations not of particles but of electromagnetic field lines. So an electromagnetic wave is caused by making fields oscillate at a source. So this means electromagnetic waves do not need particles to travel. They only need the electric and magnetic fields which permeate the entire universe. This means that electromagnetic waves can travel anywhere in the universe, even a vacuum. So electromagnetic waves can travel over the vacuum of space, so for example they can go from the sun to the earth. Now, electromagnetic waves in a vacuum can travel at the fastest possible speed in the universe, which is 3 × 10⁸ meters per second. Nothing can travel faster than an electromagnetic wave in a vacuum. Now, electromagnetic waves travel fastest in a vacuum as there are no particles present to slow the wave down. So electromagnetic waves are oscillations of the electromagnetic field, and they can travel through a vacuum. All electromagnetic waves travel at the same speed, the fastest speed in the universe in a vacuum, 3 × 10⁸ meters per second, which is commonly called the speed of light. Whilst mechanical waves are oscillations of particles, they can't travel through a vacuum. Now, mechanical waves travel at different speeds depending on the material that they are travelling in. Now, here we've got a diagram of a wave, and we can describe the transfer of energy with lots of different terms to detail wave motion, but it's very important to indicate in this diagram that the particles don't change position, rather they're vibrating backwards and forwards. So the first term we can consider is amplitude, which is measured in meters. So amplitude is the maximum displacement of particles from the equilibrium position, which is shown here on our diagram. So the equilibrium position is the rest position of the particles, or the electromagnetic field lines. The next term is the idea of wavelength, and wavelength is measured in meters. So the wavelength of a wave is the length of one whole wave cycle, and it can be measured as the distance between two peaks. So you could consider that the wavelength is the distance the wave travels before the wave repeats itself. Now, the time period is very similar to the wavelength. Time period is measured in seconds and is the time taken for one complete wave to happen. So like wavelength, it can be measured as the time it takes between two peaks. It's the distance on the actual diagram that the wave travels before it repeats itself. Now, frequency, which is measured in hertz, is the number of complete oscillations of a wave in 1 second, and this is closely linked to the time period of a wave, because frequency is equal to 1 over time period. So to recap, we have amplitude, we have wavelength, we have time period, and we have frequency. We also have another term, which is the wave speed, which is the distance travelled by each wave every second, and is measured in meters per second, but it could also be thought of as the speed in which energy is transferred by a wave. Now, just to clarify, frequency is one of the most important measurable properties of a wave, and it links to the time period of a wave and the wavelength of a wave. So remember, frequency is how many waves are produced or pass a point every single second. So what we can say is that the unit of frequency is hertz. So 1 hertz is 1 wave produced every second, and 20 hertz is 20 waves passing a point every second. And like we just said, frequency in hertz is equal to 1 over the time period in seconds. So if you have a time period of 4 seconds, what would the frequency of the wave be? Well, frequency is 1 over time period, so therefore it's 1 over 4 in this particular question, so therefore frequency is 1 over 4, which is 0.25 hertz. Now, in addition to quantities such as displacement, amplitude, wavelength, time period, frequency, there are several quantities that can be measured as differences between different waves. Because all progressive waves travel a certain distance, it's a measure of how far the energy has been propagated. Now, the difference in distances between two waves, and how much they have travelled, is called the path difference, and the path difference is measured in units of wavelength, or lambda. Now, you can also consider the position of a certain point along a wave cycle, and we call this the phase of the wave. Now, the amount by which one wave leads or lags behind another wave is called the phase difference between the waves. Now, the phase and phase difference can be measured in angles, so either degrees or radians, or you could measure it in fractions of a wave cycle. Now, we can consider a progressive wave to consist of many oscillating particles if it's in fact a mechanical wave, as shown here. Now, all of the particles will oscillate about a fixed position, and the direction of the oscillation can be given by the position in the wave. So for example, here you can see the direction in which these different particles are oscillating. So you can work out the direction of oscillation by considering the movement of the wave compared to equilibrium position. So in this progressive wave, whilst the particles oscillate, the energy is being transferred. And like we mentioned before, the phase difference is how much the particle lags behind or is ahead of another particle in a wave. So particles that are in phase are oscillating with the same displacement and are moving in the same direction as each other. So we say they have a phase difference of 0. So 2 points which are one whole wavelength apart are in phase. So 2 points which are one wavelength apart have a path difference of 1 wavelength. So what we can say is that particles which are in phase are an integer, a whole number of wavelengths apart. So the path difference for in phase particles is n lambda, where n is any integer. So the phase difference for an in-phase particle, which is now in angles, is n 2 pi radians, because there are 2 pi radians in one wavelength, or you could say n 360 degrees, because there are 360 degrees in one wavelength. Now, particles that are out of phase are oscillating with different displacements, or are oscillating in different directions as each other. So they will have a phase difference with each other. So that's an important idea to work out. So all these examples are particles which are out of phase with each other. Now, particles that are completely out of phase are particles which oscillate with the same magnitude of displacement but are oscillating in opposite direction. So we can also call this antiphase. Now, particles that are completely out of phase or in antiphase have a phase difference of pi radians, or 180 degrees, because two wavelengths that are half a wavelength apart are said to be completely out of phase. So they have a path difference of half wavelengths. So the path difference for any out of phase particle is a multiple of half wavelengths. So 1.5, 2.5, 3.5, 4.5 wavelengths, so on, so on, so on. Whilst the phase difference for an out of phase particles is n pi radians for odd values of n, because even values of pi radians will give in phase, whilst odd pi radian values will give out of phase. So you can see here, if we look at two particles of wavelength apart, such as C and G, we'll see that they're oscillating in the same time as each other, so they're completely in phase. But 2 points half a wavelength apart, such as I and K, we see they're always moving in opposite directions, so they're completely out of phase with each other. And the phase difference between the 2 points depends on the fraction of wavelength that lies between them. So like we said, when you have a path difference of greater than lambda, or a phase difference greater than 2 pi radians, which is 360 degrees, you can express your path difference or phase difference in terms of just lambda or 2 pi radians. So for example, a phase difference of 3 pi radians between 2 points on a wave is also pi radians, because it's one full cycle, 2 pi radians, plus an additional pi radians. So a phase difference of 5 pi radians between points on a wave is also pi radians, because you've had 2 full cycles of the wave, which is 4 pi radians plus that pi radians. Whilst for example, a phase difference of 6 pi radians between points on a wave is also 0, because there has been 3 whole cycles of the wave, 6 pi radians. Now we can also work out how fast a wave travels in a medium by carrying out this particular equation. Wave speed in meters per second is equal to frequency in hertz times by wavelength in meters. So this equation shows how fast a wave transfers energy throughout the universe. So the speed of a wave is the distance travelled by each wave every second in the medium. Now all waves have a finite speed because it takes time for energy to propagate from one place to another. Now in many waves, such as visible light, this time isn't perceivable to human senses, but it is present. Energy transfer is never instantaneous. So for this equation to work correctly, you've got to have a frequency of the wave in hertz and a wavelength in meters, which means you may have to convert the units given to you in a question to get to those right particular units. Now this equation makes sense when you consider what frequency and wavelength are. Frequency is the number of waves every second, and the wavelength is the length of one wave. So if you multiply the two values together, you're getting the distance travelled by the wave in 1 second, which is what the wave speed is, because we know frequency is 1 over time period and wavelength is just distance. So wave speed is 1 over time period times by distance, so therefore wave speed is distance over time period. Now the speed of all electromagnetic waves in the universe in a vacuum is 3 times 10 to the 8 meters per second. That's the fastest possible speed in the universe. Nothing can travel faster. Now it's important to note that the speed of all electromagnetic waves in a vacuum has to be 3 times 10 to the 8 meters per second. Electromagnetic waves will alter their frequency and wavelength to give a speed of 3 times 10 to the 8 meters per second. So the higher the wavelength, the lower the frequency. The shorter the wavelength, the higher the frequency. Now if an electromagnetic wave travels in a medium, it will change speed and slow down, as the electromagnetic wave is now hitting a substance. But the speed of an electromagnetic wave changes as the wavelength of the wave changes, because the frequency of the electromagnetic wave remains unchanged at all times after it has been produced. Now mechanical waves can travel at different wave speeds. Mechanical waves are movements of particles, so this means that energy travels slower than for electromagnetic waves, and the mechanical wave speed depends on the mass of the particles moving and the density of the material. Now generally we find that mechanical waves travel faster in solids than they do in fluids. That's because the particles are closer together in a solid because the material is denser, so the vibrations are more likely to result in an energy transfer. Now again, please remember that when we talk about hertz, it's just the number of complete waves every single second. So just to clarify, electromagnetic waves all travel at the same speed. This is the fastest possible speed in the universe in a vacuum, since electromagnetic waves are massless, and the speed of all electromagnetic waves in a vacuum is 3 times 10 to the 8 meters per second. Mechanical waves all travel at different speeds, since this depends on particle mass and density. Now mechanical waves contain particles with mass, so waves travel slower than electromagnetic waves. So here's an example question concerning wave speed. The wavelength of a wave is 45 meters, the frequency of the same wave is 20 meters. What is the speed of the wave? So you'd write out your equation. Wave speed is equal to frequency times by wavelength. Sub in the values, so 20 times by 45, and you get your final answer of 900 meters per second. Now in this question, we're looking at prefixes. So the wavelength of a wave is 24 millimeters. The frequency of the same wave is 31 kilohertz. What is the wave speed of the wave? So once again, you write out your wave speed equation. Wave speed is equal to frequency times by wavelength. You then substitute in your values. Now k, kilo, means times 10 to the 3. So it's 31 times 10 to the 3 multiplied by 24 millimeters. Milli means times 10 to the minus 3. So it's times by 24 times 10 to the minus 3. So we get our answer to be 740 meters per second. Let's now have a look at longitudinal and transverse waves. So as we mentioned before, a wave is a periodic disturbance in a material. Now each particle of the medium vibrates or oscillates about a fixed position, and the energy is transferred outwards from the source of a wave. So the waves that move outwards from their source are called progressive waves, and you've got two types, transverse and longitudinal. So the waves can oscillate in two different waves. So you get two different categories, transverse waves and longitudinal waves. So in longitudinal waves, the oscillations are in the same direction as the energy transfer. In transverse waves, the oscillations are at right angles to the energy transfer. So in transverse waves, each particle oscillates perpendicular to the direction of the propagation of the wave. So transverse waves can be modelled by moving one end of a slinky up and down, with each coil representing a particle. So we've got our transverse wave here showing that we've got our oscillations of the medium perpendicular to the direction in which the wave transfers energy. Now again, in a wave, the particles don't move position, they'll only oscillate. Now all electromagnetic waves are transverse, and they travel as vibrations through the magnetic and electrical fields, with the vibrations perpendicular to the direction of energy transfer. Now other examples of transverse waves include ripples on a water wave, waves on a string, in some types of earthquake seismic waves, S waves. So an example we've got here of a transverse wave is a water wave ripple. Now longitudinal waves are waves with oscillations which are parallel to the direction in which the wave transfers energy. Now again, remember, in the wave the particles don't move position, they only oscillate. So the most common example of a longitudinal wave is a sound wave. So the longitudinal waves can be modelled by moving one end of a slinky back and forth, with each coil representing a particle. Now within longitudinal waves, regions in which particles are relatively close together are called compressions, and regions where they're relatively far apart are called refractions. And this can be shown by looking at sound waves as shown here. So we can compare our two types of wave with the following diagram as shown on screen now. Now, transverse waves are waves have oscillations which are perpendicular to the direction in which the waves transfer energy. So if you assume the energy propagates from left to right, the waves oscillate up and down, and all electromagnetic waves are transverse. So electromagnetic waves are transverse waves and are the only transverse waves which can travel through a vacuum. Now they all also travel at the same speed in a medium, which is 3 times 10 to the 8 meters per second in a vacuum. So remember, electromagnetic waves are transverse waves and are produced by oscillations of the magnetic and electrical fields, so they're produced by the acceleration of movement charge. Now again, other examples of transverse waves which are not electromagnetic waves include water waves, waves on a string, and seismic waves. Longitudinal waves are waves with oscillations which are parallel to the direction in which the wave transfers energy. So if we assume the energy propagates from left to right, the waves oscillate from left to right, and examples include sound waves, P-seismic waves, and water waves as well. Now, most wave properties are shared by both transverse and longitudinal waves, but there's one that distinguishes between the two: polarization. Polarization can only happen with transverse waves. So transverse waves can be polarized, longitudinal waves cannot be polarized. So we can polarize waves with a Polaroid filter. So we can show the effect of polarization with demonstrations with Polaroid filters. But remember that polarization can only happen with transverse waves. So in 1808, Etienne Louis Mauss discovered that light waves were polarized when they were reflected. Now at the time, light waves were thought to be longitudinal, so this couldn't be explained. However, in 1817, Thomas Young understood that light waves were transverse waves, so there were electric and magnetic fields vibrating perpendicular to propagation, so this allowed for polarization to be explained. Now in our heads, when we imagine an electromagnetic wave, we think of the following. However, in reality, an unpolarized wave actually has vibrations in many different planes, each two components at 90 degrees to each other. So there are many different planes of particle oscillation. Now, polarization is removing all planes of oscillation except for one plane. So a polarized wave is a wave that oscillates in one direction only. So a Polaroid or polarizing filter can be used to polarize a wave. Now, ordinary light waves are unpolarized as they're a mixture of different vibrations and directions in the wave. Now, a Polaroid filter works as it removes all planes of wave vibration except for one. So the wave coming out the other side will mean that the image will look darker, as it literally removes all of the wave except for particle vibration in one plane. So we can set up two filters next to each other, investigate how this affects the wave. Now, two filters which are parallel to each other will allow all of the wave to pass through, so you would get a maximum intensity, because after the first filter only vertical oscillations are left in this example. So with the second filter, the vertical oscillations can pass through, so therefore they will go all the way through. Now, if the two filters are perpendicular to each other, they'll block all of the light, because the two filters will filter out the waves in all the different planes, so will completely block out the wave. So in this example, after the first filter, only the vertical oscillations are left, but at the second filter, the vertical oscillations can't pass through as they'll be removed. So this is shown in the following example here. So when it goes to 90 degrees, it's completely blocked out. And you can see it here with our rotation of our two polarizing filters. So when they're parallel, maximum intensity. When they're perpendicular, zero intensity. So we can graph the intensity of the wave that passes between both filters against the difference in angles between the filters. When the filters are perpendicular to each other, the wave intensity is at a minimum. When the filters are parallel to each other, the wave intensity is at a maximum. So you can consider a Polaroid filter like a door which has a hole in a particular plane, so it only allows that plane of oscillation through the filter and no other plane. Now, longitudinal waves cannot be polarized, because with transverse wave there's a choice in which direction the oscillations occur. So the oscillations could be in the XZ plane, the YZ plane, or anywhere in between. Now, with longitudinal waves, the oscillations only occur in one direction anyway, parallel to the propagation. So there's no need to distinguish between different oscillation directions, because there's only one oscillation directions. So the particles in a longitudinal wave vibrate in the same direction the wave travels in. So there's no possibility to isolate a particular direction of vibration from it. So polarization is just not possible in longitudinal waves. So if a wave can be polarized, it is proof that it must be a transverse wave. Now, light waves that reflect off some surfaces are partially polarized. So light, when it's reflected off surfaces like water or glass, can cause glare. Now, as reflected light is partially polarized, it allows us to filter some of it out using polarizing filters. So if you view partially polarized light through a polarizing filter at a right angle, it can block out some of this reflected light whilst letting some of the light through, which will vibrate at the angle of the filter. So what it will do is it will reduce the intensity of the light entering your eye, and it is used in some sunglasses. In addition, TV signals are polarized by the orientations of the rods on the transmitting aerial, because there are two types of transmitting TV aerial, the horizontally aligned aerial and the vertically aligned aerial. So to receive a strong signal, you've got to line the rods on your receiving aerial with the rods on the transmitting aerial. So if they're not aligned, the signal strength will be lower, and it's the same with radio signals as well. So if you try to tune a radio signal and then move the aerial around, the signal will come and go as the transmitting and receiving aerials go in and out of alignment. Now, polarization does have many uses in the real world. So it can be used in sunglasses to reduce glare. It can by reducing the partially polarized light created when light is reflected by things like water and glass. Also, filters can be used by photographers to alter the appearance of things like the sky, and polarization can be used in the stress and strain analysis of certain plastics like perspex, whilst also polarized light micrography is a useful technique to analyze crystal structures. Let's now finally look at the principle of superposition. So like mentioned before, a progressive wave is a transfer of energy due to the oscillations of particles or fields. So a progressive wave will carry energy from one place to another without transferring any material. A progressive wave consists of oscillations passing through a medium or field carrying energy with it, and a progressive wave transfers energy away from a source so that the source of the wave will lose energy. But there is another type of wave, which is a stationary wave. Now a stationary or standing wave is a superposition of two progressive waves. So the two progressive waves have to be what we call coherent with each other, have the same frequency, wavelength and amplitude, and the two progressive waves must be moving in opposite directions with each other. Now unlike progressive waves, no energy is transmitted by a stationary wave, rather the energy is displayed. Now superposition happens when two or more waves pass through each other. Now because they are vectors, they will add when they overlap. Now superposition is an example of what we call interference, and interference is a property that all waves demonstrate. Now before the superposition takes place, the progressive waves head towards each other. At the instant the waves cross and overlap, their displacements will combine from each wave, whilst after the superposition each wave continues on its way. Now the principle of superposition is that when two or more waves overlap, the resultant displacement equals the vector sum of the individual displacements of each wave. Now only coherent progressive waves can interfere. Now coherency between waves is obtained when the waves have a constant phase difference and the same frequency. So the superposition of waves can result in interference. Now when two waves meet, if their displacements are in the same direction, the displacements combine to give a bigger displacement. So for example, a crest plus a crest gives a bigger crest. A trough plus a trough gives a bigger trough. Now this is called constructive interference. Now points on waves will constructively interfere when there's a phase difference of 2 pi radians or any multiple of that, when the two waves are in phase, when the path difference between the waves is a multiple of the wavelength of lambda. Now if a wave with a positive displacement meets a wave with a negative displacement, they'll cancel each other out. The displacement of the combined wave is found by adding the displacements of the two waves. So if one's a plus and one's a minus, they'll equal out, if it's the same value, to be 0. Now this is called destructive interference if they just cancel through, but if they cancel through completely to equal 0, we call it total destructive interference. Now total destructive interference will occur when points on waves have a phase difference of pi radians or any multiple of that. They're completely out of phase. So the phase difference is that of half a wavelength or any multiple of that. Now a stationary wave can be produced on a string by setting up a driving oscillator at one end of a stretched string with the other end fixed, as shown here. Now a wave can be produced by the oscillator and sent down the string. The wave will then reflect off the fixed point and come back in the other direction, and the two waves will interfere with each other and produce a stationary wave. Now the two waves will interfere with each other as they're coherent with each other and they're overlapping and they're moving in opposite directions. So the two waves interfere with each other and produce a stationary wave, as shown in this particular animation. So what you can see here is you've got your stationary wave. So for most frequencies, the resultant pattern will be a jumble. However, if the oscillator happens to produce an exact number of waves in the time it takes for a wave to get to the end and back again, the two waves will reinforce each other. Now the frequencies at which this happens is called the resonant frequencies. These cause stationary waves when the overall pattern stays constant. The string just vibrates up and down, making loops. Now note, by the way, you'll get the following wave pattern for transverse waves. Now the nodes are the points on the standing wave where the amplitude of vibration is 0, the particles don't move. So the particles have no energy at the nodes. Now the nodes are half a wavelength apart on a standing wave, and nodes are caused by total destructive interference between the two progressive waves. Now antinodes are points on the standing wave where the amplitude of vibration is a maximum. So the particles have maximum energy at antinodes. So the antinodes are half a wavelength apart on a standing wave, and antinodes are caused by the constructive interference between two waves. So let's now just consider the differences between the progressive and stationary waves. So with stationary waves, the amplitude of vibration varies with position, but for progressive waves, the amplitude of vibration is the same in every position. For stationary waves, nodes and antinodes don't move along the wave, but for a progressive wave, crests and troughs do move along the wave. For stationary waves, between adjacent nodes, all the points are in a vibrating phase with each other, but for a progressive wave, the phase varies continuously along the wave. And for stationary waves, only resonant frequencies support stationary waves, whilst all frequencies support progressive waves. So as we said before, stationary waves are not formed at all frequencies. Stationary waves only form at exact resonant frequencies. So resonant frequencies occur when an exact number of half wavelengths fit on the string, and these frequencies are called harmonics. Now the first harmonic is when the wave is vibrating at its lowest possible resonant frequency. So you'll notice from this diagram it has a loop with a node at each end. So in this example of the first harmonic, one half wavelength fits onto the string, so the wavelength is double the length of the string. So as we say the frequency is f0, the length is lambda over 2, so therefore the wavelength is 2L. Now the second harmonic is twice the frequency of the first harmonic. There are two loops with a node in the middle and one at each end, so two half wavelengths fit on the string, so the wavelength is the length of the string, as shown here. The third harmonic is 3 times the frequency of the first harmonic, and you'll notice here that there are 1.5 wavelengths on the string. So the frequency is 3 times the frequency of the first harmonic, the length of the string is 3 over 2 wavelengths, and the wavelength is therefore 2 over 3 lengths of the string. Now you can have as many harmonics as you like, but the frequency of any harmonic must be a multiple of the first harmonic's frequency. Now the properties of harmonics follow the following pattern. For the nth harmonic, the number of nodes is equal to n plus 1. The number of antinodes is equal to n. The frequency of the nth harmonic is n times by the frequency of the first harmonic. The length is equal to n over 2 times by lambda, and the wavelength of the nth harmonic is 2L over n. So this information can be used to sketch the stationary wave pattern of the harmonic. So for the 6th harmonic, with the first harmonic having a frequency of 20 Hz, the number of nodes will be 6 plus 1, which is 7. The number of antinodes will equal 6. The frequency will be 6 times by 20, 120 Hz. The length will be 6 over 2 lambda, so 3 lambda, and the wavelength will be 2L over 6, which is L over 3. Now you can produce stationary waves by reflecting a microwave beam at a metal plate. The superposition of the wave and its reflection produces a stationary wave, and you can find the nodes and antinodes by moving a probe between the transmitter and the reflecting plate. The probe will receive no signal at the nodes and a maximum signal at the antinodes. Now powder in a tube of air can produce stationary sound waves. A loudspeaker can produce a stationary sound wave in a tube, and the powder is laid along the bottom of the tube, is then shaken from the antinodes but left undisturbed at the nodes. Now a number of factors affecting resonance frequencies that can be produced on a particular string. Now these include the length of the string, the mass per unit length of the string, and the tension of the string. Because the longer the string, the lower the resonant frequencies, because the half wavelength is longer. The more the mass per unit length of the string, the lower the resonance frequencies, because the wave travels more slowly down a heavier string. And the lower the tension on the string, the lower the resonant frequency, because the wave travels more slowly down a loose string. So we can express all these particular factors in this equation. F is equal to 1 over 2L times by the square root of T over mu, where F is the resonant frequency of the first harmonic in Hertz, L is the length of the vibrating string in meters, T is the tension the string is under in newtons, and mu is the mass per unit length of the string in kilograms per meter. So the longer the string length, the lower the resonant frequency. The higher the mass per unit length, the lower the resonant frequency, and the larger the tension, the higher the resonant frequency. So let's summarise what we've looked at in this particular revision session. We looked at the idea of the oscillations of particles in a medium with amplitude, frequency, wavelength, speed, phase difference, and frequency is 1 over time period. Now phase difference may be measured as angles or fractions of a cycle. Now in addition, we know that the speed is equal to f lambda, and that you can investigate the factors that determine the speed of a water wave. You should know the nature of longitudinal and transverse waves, including examples of each with sound, electromagnetic waves and waves on a string, and you'd be expected to know that the direction of the displacement of particles and fields are relative to the direction of energy propagation, and that all electromagnetic waves travel at the same speed in a vacuum. You should understand polarization as evidence for transverse waves, and applications of polarizers to include the Polaroid material and the alignment of areas for transmission and reception. We should also be aware of stationary waves, nodes and antinodes on strings, knowing the equation F is equal to 1 over 2L times by the square root of T over mu for the first harmonic, that there's a formation of stationary waves by two waves of the same frequency travelling in opposite directions. You will also expected to understand a graphical explanation of the formation of stationary waves, that stationary waves formed on a string and those produced with microwaves and sound waves can be considered, and that stationary waves on strings will be described in terms of harmonics, but we don't use the term fundamental or overtones in our descriptions. So, thank you very much. Hello and welcome to this revision session on refraction, diffraction and interference, which is part of the waves topic in AQA A-level physics. So in today's revision session we're going to be looking at the following parts of the AQA physics specification: 3.3.2.1 interference, 3.3.2.2 diffraction and 3.3.2.3 refraction at a plane surface. So we'll start off in this revision session by looking at the concept of interference. Now, superposition is a phenomenon that happens in waves, which happens when two or more waves pass through each other. Now, because the waves are vectors, they'll add when they overlap. Now, superposition is an example of interference, and interference is a property of all waves. Now, before in this situation, the progressive waves head towards each other. At the instant in which the waves cross and overlap, the displacements due to each wave combines, and then after this process happens, each wave continues on its way unaffected. Now, the principle of superposition is that when two or more waves overlap, the resultant displacement equals the vector sum of the individual displacements. But it's important to note that only coherent progressive waves can interfere. Now, coherency between waves is obtained when waves have a constant phase difference and the same frequency and wavelength. Now, the superposition of waves, as mentioned before, can result in interference. So when two waves meet, if their displacements are in the same direction, the displacements combine to give a bigger displacement. So for example, a crest plus a crest gives a bigger crest, and a trough plus a trough gives a bigger trough. Now, this concept is called constructive interference. Now, points on waves which constructively interfere have a phase difference of 2 pi radians or any multiple of that, so we say that they are in phase. So we can also say that points on waves that constructively interfere have a path difference of a wavelength or multiples of a wavelength. They again are in phase. Now, if a wave with a positive displacement meets a wave with a negative displacement, they will cancel each other out. Now, the displacement of the combined wave is found by adding the displacements of the two waves. Now, this is called destructive interference. Now, if two waves with equal yet opposite displacements meet, so for example a crest and a trough with equal magnitudes overlap with each other, they will cancel each other out completely. Now, this is called total destructive interference. Now, points on waves which totally destructively interfere have a phase difference of pi radians or a multiple of pi radians for odd numbers, okay, and they're completely out of phase. Or we can say that they have a path difference of half wavelengths or multiples of half wavelengths, so 1.5, 2.5, 3.5. They're completely out of phase. Now, to see two source interference with light, you can either use two coherent light sources or shine a laser through two slits. Now, a laser is a source of monochromatic coherent light. Now, you can create two coherent sources by using a single laser by shining that laser beam through a card containing two slits. So it's important to note that you can create those sources by putting that laser beam through those two slits. Now, as the light wave passes through each slit, the light will diffract. Now, to ensure diffraction takes place, the wavelength of the wave source must be similar to the gap of the slit in your little double slit there. Now, the two waves interfere and create a pattern of constructive and destructive interference on the screen. Now this is shown as bright and dark fringes. So the two waves interfere and create a pattern of constructive, which give the bright fringes, and destructive interference, which gives the dark fringes on the screen. Now you can see that this experiment is referred to as the Young double slit experiment. This is because Thomas Young was the first person to carry out this experiment, and he used white light instead of a laser. Now you can determine the path difference and phase difference between the two sources in each interference pattern. Now, as mentioned before, the experiment can be carried out with a laser, as it tends to be in the modern world, or you can carry it out with a white light source like Thomas Young did originally in the 19th century. Now when a white light source is used, the pattern is less intense and has a wider maxima. Now in addition, when a white light source is used, the pattern will contain different colours but have a central white fringe, as white light is made up of many different frequencies. It is not monochromatic. Now the Young double slit experiment is a very important experiment in the history of physics because it provided evidence that light could act as a wave. It showed that light could both diffract and interfere, which are both wave mechanisms. So this backed up the theory of Huygens, who earlier had stated that light must be a wave. Now this contradicted the theory proposed by Isaac Newton, which suggested that light waves were made out of particles, which Newton himself called corpuscles. Now this leads to the Young double slit experiment being one of the most important experiments in the history of science. It was one of the first experimental proofs that light must act as a wave. Now you can derive an equation regarding this experiment by considering the following setup. Now you can say S is the distance between the centres of two slits, W is the separation between the centres of two bright or two dark fringes which are adjacent to each other, and big D is the distance between the slit and the screen. Now P, as you can see on this diagram, is the first bright fringe on the screen. Now if we use the purple triangle as shown on the screen, you can see that sine theta is equal to opposite over adjacent, a bit of trigonometry. So in this case it equals the path difference divided by the slit separation. Now we know the path difference in this case is one wavelength because it's our first order bright fringe, so as a result it's only one wavelength difference, and we know the slit separation is S. Now because theta is very small, we can use something called the small angle approximation to state that sine theta is actually just equal to theta. So with this idea we can say theta is equal to lambda over S. Now if we now consider the yellow triangle as shown on the screen, we can say that tan theta is equal to opposite over adjacent, which in this case is the fringe spacing divided by the distance between the slit and the screen. So we can say that it equals W over big D. Now again, as theta is very small, we can say tan theta equals theta, so therefore theta equals W over D. Now we can combine both these equations because they're both equal to theta, so we can say W over D equals lambda over S. So we can rearrange that to say W is equal to lambda D over S. So this allows us to calculate values for the Young double slit experiment, where W is the fringe spacing, the distance between two adjacent bright or dark fringes on the screen in meters. Lambda is the wavelength of the wave source in meters. D is the distance between the slit to the screen in meters, and S is the distance between two slits centre to centre in meters. Let's now have a look at the concept of diffraction. So diffraction is the process of a wave spreading out as they come through a narrow gap or go around an obstacle. Now that's very important, as you can see in the following diagram. So it's very important to note that diffraction can easily be observed through water waves in a ripple tank. Now again, it's very important to note that the diffraction is the process of a wave spreading out as they come through a narrow gap or go around an obstacle. Now all waves will diffract, and the amount of diffraction depends on the wavelength of the wave compared to the gap size it moves through. So you can say that when the gap is a lot bigger than the wavelength, diffraction isn't a very noticeable effect. But you do get get a noticeable effect of diffraction when the gap is several wavelengths wide, and the most diffraction takes place when the gap size is the same size as the wavelength of the wave. Now, if the gap is smaller than the wavelength, the wave actually mostly reflects, and most of which goes through will diffract, but there's not much for going through to diffract. So it's important to note that like sound waves will diffract a lot when they move through a door frame, as the wavelength of the sound wave is about the same size as the gap size of the door frame. But light waves will not diffract when moving through a door frame, as the light wave has a much smaller wavelength than the gap of the door frame. So for light waves to diffract, they must pass through a very small gap or slit, because that gap or slit must be equivalent to the wavelength of light, which is a very, very small value in meters. So if light is shone through a narrow slit, it can produce a diffraction pattern. But to get a clear diffraction pattern, you should use monochromatic light which is coherent, and it's important to know that monochromatic is a light source containing a single wavelength or frequency. Now, if the light is not monochromatic, it'll have numerous wavelengths and numerous frequencies, so different wavelengths will be diffracted by different amounts, so the pattern produced would not be very clear. So to get monochromatic light, you can either put a filter in front of white light or use a laser source, and in fact the laser source will give a clearer pattern than using white light which has been filtered. Now, as a laser beam is coherent, it is very powerful and can damage your eyesight, so you should never shine a laser towards a person or off a reflective surface. You should always wear safety goggles when using a laser and have a warning sign on display. Also, the laser should never be left on when not in use. So you can see here, when you shine light through a single slit, you can produce the following diffraction pattern, which you can observe as the following here. Now, if the wavelength of light is similar to the size of the slit it passes through, you'll get a very consistent and a clear diffraction pattern of bright fringes, which are maxima, and dark fringes, which are minima. Now, this fringe pattern is due to interference taking place after the diffraction process. Now, the pattern has a bright central fringe, which we call the central maxima, with alternating bright and dark fringes on either side of it. Now, the bright fringes, or the maxima, occur due to constructive interference. The waves from across the width of the slit arrive at that point on the screen in phase. Now, the dark fringes, or the minima, occur due to destructive interference. The waves from across the width of the slit arrive at the point on the screen completely out of phase. Now, you can see here that when you put your white light shone through a narrow slit, you can get the following diffraction pattern, which you can observe with this particular image as well. Now, you'll notice that when white light is shone through the slit, the different wavelengths are diffracted by different amounts, and the longer the wavelength, the greater the diffraction. So red light would diffract the most, and blue and violet light would diffract the least. And you can see here in this particular image that you're going to get a variance in where the colours lie because of the amount of diffraction that takes place. Now, instead of getting clear fringes, you get a spectra of colours at each maxima, so the colours spread out as a spectrum, but it's not observed at the central maxima, and this stays white. Now, the central maxima is the brightest part of the pattern. Now, that's because the intensity of the light is highest at the centre. So for monochromatic light, all photons have the same energy, so this means there's more energy hitting the centre every single second, given a more intense part of your pattern. Now, you'll notice as well that the width of the central maxima varies with the width of the slit and the wavelength of the light. Now, increasing the slit width will decrease the amount of diffraction, so this means that the central maxima is narrower and the intensity of the central maxima is higher, because your diffraction pattern has narrowed up and squashed in together. Whilst increasing the wavelength of the light source will increase the amount of diffraction, so it will cause your diffraction pattern to spread out. So this means that the central maxima is wider and the intensity of that central maxima is lower, because that light source has now been spread out over a greater distance. Now, previously, when we've considered the diffraction pattern produced when waves are passed through the double slit, we can see that we can get the following interference pattern, which we've said before is the Young double slit experiment, which again, if you put onto the screen, you can see the following maxima and minima produced on the screen after the laser source or light source has passed through the double slit. Now, you can also carry out this experiment experiment, but using more than just two equally spaced slits. So this includes something called a diffraction grating. Now a diffraction grating contains lots of equally spaced slits very close together, okay, and can be used to mimic this particular effect. Now the pattern produced from a diffraction grating is basically the same as the one produced with the double slits, except the brighter bands are brighter and narrower, and the darker bands between them are darker, so your diffraction pattern ultimately is a lot sharper, as shown in this particular image. So you can see with the more slits used in your diffraction grating, the sharper and sharper the diffraction pattern is produced on the screen. So in a diffraction grating there are many equally spaced slits at right angles to the wave. So when monochromatic light is then passed through the diffraction grating, an interference pattern will form on the screen behind it. Now the interference pattern produced, as mentioned before, is really sharp because there are many beams passing through the grating and reinforcing the pattern. Now having a sharper pattern is really good because it allows for more accurate measurements to be taken by experimenters. Now for monochromatic light, all the maxima in the diffraction pattern are formed in sharp lines. Now we identify each line of maxima or maximum brightness as an order of maxima, given the symbol n. Now the line at the center of the pattern is in the same plane as the beam incident on the grating, so we call that the zero order line, n equals 0. So you can see on this diagram the zero order line is the maximum brightness order produced at the dead center. Now the lines at either side of the central zero order line are called the first order line, as shown on this particular diagram, and the lines either side of the first order lines are called the second order lines, and that will go on and on and on. Now we can derive a relationship between the angle between the order of diffraction and the zeroth order, and the wavelength of the wave, the order of the diffraction, and the distance between the slits. So when a wave passes through the slits of the diffraction grating, the path difference at the zeroth order maximum is 0 because they're in phase, because you're getting a constructive interference. Now at the first order maxima there's also constructive interference, and the path difference between the two waves is one wavelength because they are in phase, so you get a bright fringe being formed. So the wave from one slit lines up with the waves from the next slit because they're exactly one wavelength difference in their path. So that tells us that for the nth order maxima, the path difference is equal to n, the order, multiplied by the wavelength. Now if we then consider the triangle shown in the diagram, we can use trigonometry to derive an expression. We can say that sine theta is equal to opposite over hypotenuse, so it equals to lambda over d, where lambda is the path difference and d is the slit separation. Now we know for the first order of diffraction, where n equals 1, sine theta 1 equals lambda over d. Then for the second order of diffraction, where n equals 2, sine theta 2 equals 2 lambda over d. So that tells us that for the nth order of diffraction, sine theta n equals n lambda over d. So we can rearrange this to get to the diffraction grating equation. D sine theta is equal to n lambda, where d is the distance between the slits in meters, lambda is the angle to the normal made by the maximum in degrees or radians, n is the order of diffraction or order of maximum, and lambda is the wavelength of the wave source. Now many diffraction gratings are in fact not labelled with d, but are labelled with the number of slits found per millimeter. Now to work out d in meters is equal to 1 over the number of lines found in 1 meter for your diffraction grating. So for example, if there are 3 times 10 to the 5 slits for every meter in your diffraction grating, d is equal to 1 over 3 times 10 to the 5, which is 3.33 times 10 to the minus 6 meters. Now the maximum angle to see orders of maxima is when the beam is at right angles to the diffraction grating. So that means we would set theta is equal to 90 degrees, so therefore sine theta equals 1. So the highest order of maxima visible to the experimenter is calculated by the equation n equals d over lambda, because sine 90 is equal to 1. Now since n must be an integer, if the value is a decimal it must be rounded down. So if you get your n to be calculated to be 3.33, 0.2, then n equals 3 is the highest visible order observed. Now from this equation it tells us that if lambda is bigger, then therefore sine theta is bigger, so theta in general is bigger. So this therefore means that if you increase your wavelength, that the diffraction pattern produced will spread out. Whilst if d is bigger, it tells us sine theta is smaller, so therefore theta is smaller. So this means that the coarser the grating, the less the pattern will spread out. Now diffraction gratings are very useful in the real world for separating light of different wavelengths with a high resolution, because if you diffract white light through a diffraction grating, then the patterns due to the different wavelengths within the white light are spread out by different amounts. So you can see here that each order in the pattern becomes a spectrum, with red on the outside to the central maxima and violet on the inside to the central maxima. Now the 0th order maximum stays white because all the wavelength for that point just passes straight through. Now we can use this in many different examples. In spectrometers we use them to analyze light from stars, to allow us to analyze the composition of a star, just general chemical analysis, and also to measure redshift and rotation of stars, measure the frequency and wavelength of light from any star in the universe, observe the spectra of materials, and analyze absorption and emission spectra in stars. Because when you split up light from a star using a diffraction grating, you see absorption line spectra, which is spectra with dark lines correspond to different wavelengths of light that have been absorbed by the atmosphere of that star. Now each element in a star's atmosphere has a different absorption spectra, so astronomers can use this to identify the different elements found in the atmospheres of stars. In addition, diffraction gratings also play a role in X-ray crystallography. X-rays are directed at a thin crystal sheet which acts as a diffraction grating to form a diffraction pattern. That's because the wavelength of the X-ray is similar in size to the gaps between the atoms in size. So this diffraction pattern can be used to measure the atomic space in certain materials. So your crystal acts like a diffraction grating, and the space between the atoms is equivalent to the wavelength of the source, so it allows us to form a diffraction pattern. Now one of the major discoveries using X-ray crystallography was the structure of DNA and its double helix-like nature. Let's now have a look at the refraction at a plane surface. So when a wave meets a boundary between two materials, in general some of its energy is reflected and the remainder is transmitted into a new medium, as shown in this particular diagram. Now the principle of conservation of energy means that at the boundary between two materials, the energy of the reflected wave added to the energy of the transmitted wave must therefore equal the total energy of the incident wave. Now the wave speed depends on some of the properties of the medium, so as a wave crosses a boundary between two different materials, it'll either speed up or slow down. So for example, light travels at a higher speed in air than it does in water or glass, and water waves slow down as they move from deep water to shallow water. Now refraction is the change in the direction of a wave that occurs due to the change in wave speed as it travels from one medium to another. Now an example of this is when sound waves refract. Sound waves travel faster in warmer air compared to colder air. So at a night time you find that the air near the ground is warmer than air higher up due to human activity, so sound waves will travel faster in warmer air, so will curve back down towards the ground at night. And this is why you can often hear things better at night time compared to the daytime. Now it's important to note that when a wave slows down, the wavefronts of your wave get closer together, which is shown in the following diagram. Now this is to be expected because wave speed is equal to frequency times by wavelength. Now the frequency is always determined by the source of the wave, so therefore will remain constant in this particular example. So this tells us that if c equals f lambda and f remains constant, that if speed decreases, then wavelength lambda must also decrease. Now technically as well, the intensity and amplitude of the wave also decrease slightly upon refraction, since a small portion of the wave also reflects, but this is not as noticeable as the change in speed and wavelength during the refraction process. Now a wave will change direction when it enters a new medium, as it hits the medium at an angle. Because when the wave strikes the boundary at an angle, part of the wavefront reaches the new medium before the rest of the wave, and that part will therefore change speed first, and it will slow down in this instance before the rest of the wavefront. Now as the rest of the wavefront enters the medium and slows down, the wavefront changes direction, so therefore it has been refracted. So when a wave enters a more more dense medium, it will slow down and deflect towards the normal, and vice versa when it goes into a less dense medium. Now the change in angle depends on the ratio of the wave speed in each medium. The bigger the change in wave speed, the bigger the change in angle. Now, the absolute refractive index n is a property of a material which measures how much light slows down when it passes through it. Now, it can also be thought of as the ratio between the speed of light in a vacuum c and the speed of light in a material cs. So therefore the absolute refractive index is equal to c over cs, where c is the speed of light in a vacuum, 3 times 10 to the 8 meters per second, and cs is the speed of light in the substance. Now the absolute refractive index of a material is a property of that material only, because light travels at different speeds within different substances, which depends on the refractive index. So therefore a material with a high refractive index is called optically dense, and such material can cause the light to travel a lot slower. So if you were given a question and might say the refractive index of plastic is 1.47, what is the speed of light in the plastic? Well, we say n equals c over cs, so therefore cs is c over n by rearrangement. C is equal to 3 times 10 to the 8, and in this instance n equals 1.47. So therefore the speed of light in the plastic is 2.04 times 10 to the 8 meters per second. Now here are some examples of some refractive indices of different materials. Now the slower the speed of light in the material, the higher its refractive index. Now since the speed of light in a substance will always be less than the speed of light in a vacuum, the value of n will always be greater than 1. So materials with a high refractive index are referred to as being optically dense. Now in calculations, the refractive index of air can be taken to be approximately 1.003. Now this indicates light does not slow down significantly when travelling through air as opposed to travelling through a vacuum. Now the value of the refractive index of air does depend on the density of air, which does vary with temperature. Now you should always double check for calculations in refractive index that your value is always greater than 1. Now when light is refracted at the boundary between two materials, the amount of refraction depends on the ratio of refractive indices of the two materials, as shown in this particular diagram. Now we call this θ1 the angle of incidence, and is always measured from the normal to the ray, and we call this angle θ2 the angle of refraction, and once again it's always measured from the normal to the reflected ray. Now the Snell's law links the angles of incidence and refraction with the speed of light in each medium. Now from observation, light will move towards the normal if it passes from a less optically dense material into a more optically dense material. So when n2 is greater than n1, θ2 is greater than θ1, and it's the converse if it moves into a less optically dense material. n1 will be greater than n2, so θ2 will be greater than θ1. Now Snell's law for refraction for a boundary between two materials is given by the equation n1 sine θ1 equals n2 sine θ2, where n1 is the refractive index of the first material light is in, n2 is the refractive index of the second material light is in, θ1 is the angle of incidence of the ray in the first material to the normal, and θ2 is the angle of refraction to the normal in the second material. Now like mentioned before, θ1 and θ2 are always taken from the normal. Material 1 is always the material that the ray goes through first, and material 2 is what the ray goes through second. Now we can say that n1 n2, which is n2 over n1, is known as the relative refractive index, and this is a ratio between the two refractive indices, so therefore it has no unit, it is just a number. It is also the ratio of the speed of light in material 1 compared to the speed of light in material 2. So you can also write the relative refractive index is equal to c1 over c2. So we can equate these and say c1 over c2 equals n2 over n1, and you can use this equivalence between the refractive index ratio and the speed of light ratios to work out values if needed. Now the relative refractive index is a property of the interface between the two materials, and it's different for every two possible pairings of materials. Now if the two materials have the same refractive indices, well then the relative refractive index would be 1. So in this case the refraction would be perfect, so it would fully deflect the wave without distortion, which would make the second material invisible. Now that tells us an invisibility cloak would work if the refractive index is always identical to the surroundings. Now we know from Snell's law n1 sine theta 1 equals n2 sine theta 2. Now for this to be true, the incident ray, refracted ray and the normal must all lie in the same plane. Now this law is based on Fermat's principle, which indicates that light will take the path that minimizes its journey time in any material. Now when you're answering questions, always check that the angle of incidence and the angle of refraction are the angles between the normal and the light ray. If the angle between the light ray and the boundary is calculated instead, you do 90 minus theta to get the correct angle. So an example question here indicates to us, it's asking us to calculate the refractive index of material 2, given that in material 1 you've got a refractive index of 1.2. So you do n1 sine theta 1 equals n2 sine theta 2, you pop your numbers in and you work it through and you get n2 to be 1.65, which makes sense because it has refracted towards the normal, so it's traveling slower, so it must be in a material of a higher refractive index, which the calculation suggests it is. Now when a light ray travels from one medium to a less optically dense medium, it's refracted away from the normal. So the angle of refraction is larger than the angle of incidence. So you can see in this instance that taking place. Now the larger the angle of incidence, the larger the angle of refraction. So as you increase the angle of incidence, the angle of refraction gets closer and closer to 90 degrees. Eventually, the angle of incidence, when you keep increasing it, will eventually allow the angle of refraction to equal 90 degrees. So eventually the light will refract along the boundary. Now when this happens and the angle of refraction is 90 degrees, the angle of incidence is called the critical angle. Now for this to happen at any boundary, the light must be passing from a more optically dense material into a less optically dense material, or going from a high refractive index material to a material with a lower refractive index. So for this to take place, we can say n2 is greater than n1. Now we can work out the critical angle for a boundary with the equation that sine theta c, or sine critical angle, is equal to n2 over n1, where n1 must be greater than n2, is shown with this particular screen here. Now you can derive this formula by arranging Snell's law by saying n1 sine theta 1 equals n2 sine theta 2. So we pop the sine thetas and the n's onto the same side of each equation. Now we know at the critical angle that the angle of incidence is equal to the critical angle and the angle of refraction is equal to 90 degrees. We know sine 90 is equal to 1, so therefore we can say n2 over n1 equals sine critical angle, as shown in our equation. Now remember, the refractive index of air is 1, so this can simplify this equation for any material which has air as a boundary. So if we state that we know that the material to air boundary is going to be 1, we can say n2 is equal to 1 over sine theta critical angle. Now for angles of incidence greater than the critical angle, refraction cannot take place. So this means all of the light is reflected back into the material, as shown in this particular diagram. Now this is called total internal reflection. This is total because all of the incident light energy is reflected back into the material. Now there are two conditions for total internal reflection. The angle of incidence must be greater than the critical angle, and the refractive index n1 must be greater than the refractive index n2. So a question could ask you to find the critical angle of the glass to air boundary if the glass had a refractive index of 1.5. So we say sine critical angle equals n2 over n1. So sine critical angle equals 1 over 1.5, so the critical angle equals 42 degrees. Now another question could be, a plastic block is immersed in a liquid. If the refractive index of the liquid is 1.40 and the critical angle of the light travel from the plastic to glass is 79.1 degrees, what is the refractive index of the plastic? So we say sine theta c equals n2 over n1. We can then rearrange to find n1 to be n2 over sine theta, so it's 1.4 over sine 79.1 equals 1.43. Now fibre optics utilise the phenomena of total internal reflection to send high-speed light signals over large distances. So you can see here a diagram of a standard fibre optic. Now fibre optics have many important uses, including communication such as telephone and internet transmission, but also medical imaging such as endoscopes. Now fibre optics have many advantages for transferring information over the traditional copper wires. They can carry more information, the light will not heat up the fibre, there's no electrical optical interference, the fibre optics are cheaper than copper wires and the signal can travel very quickly. So for a fibre optic to work, light is shone in at one end of the fibre. The light hits the boundary between the fibre and the cladding at an angle greater than the critical angle. This ensures the light travels down the cable, carrying out total internal reflection. So this ensures the light completes the entire journey inside the fibre optic and no light is transmitted out of the fibre optic. Now there are three main components that make up optical fibres: an optically dense core such as plastic or glass, and a lower optically dense material which is a cladding surrounding the core, and an outer sheath as shown in this particular diagram. Now a fibre optic which has a cladding with a lower refractive index than the core is called a step index fibre optic. Now since the refractive index of the core is greater than the refractive index of the cladding, this allows total internal reflection to occur. So in this we can see an example of a step index fibre optic. Now the outer sheath is important because it prevents physical damage to the fibre, it strengthens the optical fibre, and it protects the optical fibre from outside damage such as scratches. Now the cladding is important because it protects the core from damage, it prevents signal degradation as from light escaping the core which can cause information to be lost, it keeps signals secure and maintains the quality of the original signal, it can prevent scratching of the core, and it keeps the core away from adjacent other fibre optics, preventing the crossover information to other fibres. So it can also provide the fibre with strength and prevent breakage, given the core has to be very, very thin. Now the core of your fibre optic allows the transmission of light in the fibre optic with little absorption taking place. Now information is sent down optical fibres as pulses of light, which makes up the information signal, is shown in this diagram. So you can see in this particular image that the angle of incidence must be greater than the critical angle, and that the refractive index of the cladding must be lower than the refractive index of the core. Now when the reflection is taking place inside the core, the angle of incidence must equal the angle of reflection. Now over time, when this information is sent down the fibre optic by total internal reflection, the signal is degraded by the process of absorption or dispersion, which can cause information to be lost from the fibre optic. Now absorption is where some of the signal's energy is absorbed by the material the fibre is made from. So this can cause the amplitude of the signal to drop. So the energy loss results in the amplitude being reduced, which can lead to a loss of information in the signal. Now absorption can also be caused by the signal being attenuated in the core. Now to reduce absorption, you've got to use a core which is extremely transparent and use optical fibre repeaters so that the pulse is regenerated before significant absorption takes place. The other issue in fibre optics is pulse broadening. Now pulse broadening is when the received signal is broader than the initial signal, so you can see that it's spread out and it's over a longer area than it was originally. Now broadened pulses can overlap each other, which can lead to information being lost, because would lead to the final pulse of information being distorted when received at the other end. Now pulse broadening can be caused by both material and modal dispersion. Material dispersion or spectral dispersion occurs when white light is used in your fibre optic instead of monochromatic light. This is because different wavelengths of light travel at different speeds. Blue light travels at a slower speed than red light due to having a greater refractive index, so red light would reach the end of the fibre optic core before the blue light. So this would cause the different colours of light to spread out in your fibre optic as they're travelling down, as shown in the following diagram. So this would cause the pulse of the information to be a lot broader at the end compared to the start. Now to reduce material dispersion, monochromatic light can be used to prevent this from taking place. Now modal dispersion occurs when the light pulses in the optical fibre spread out due to the different angles of incidence in the original pulse. So there'll be different paths for the different light rays to travel. Now this is more prominent in wider cores, as the light travelling along the axis of the core travels a shorter distance than the light undergoing total internal reflection at the boundaries. Now this can also cause pulse broadening, as the pulses emerging are longer than they should be, as shown in the following diagram. This causes your pulse to spread spread out. Now, to prevent modal dispersion, the core needs to be very narrow. So this means that the core only has one path. It's a single mode fibre. So you can see here the causes of material and modal dispersion and what can be done to prevent each one. Now, both material and modal dispersion can lead to pulse broadening taking place. Now, if a fibre does not have a narrow core, then there are multiple paths or modes that light rays can take in the core, as shown in the following diagram. Now, you'll notice that axial rays travel straight down the middle of the fibre, whilst non-axial rays reflect off the side of the fibre. Now, because they're travelling a much shorter distance with the same speed, axial rays travel much faster than non-axial rays. So this can cause pulse broadening because the two rays will reach the end at different times. Now, this can be prevented by having a narrow core, a single mode fibre, but it can also be reduced by having a small difference in the refractive index between the core and the cladding, because this process will then give a large value for the critical angle, so it gives fewer potential paths for the light rays to travel down. Now again, remember, for total internal reflection to take place at all, the refractive index of the core must be higher than that of the cladding. So to summarise what we've looked at in today's revision session, we should be able to understand path difference and coherence and understand interference and diffraction using laser as a source of monochromatic light. We should be able to use the Young double slit experiment with the use of two coherent sources or the use of a single source with double slits to produce an interference pattern where W, the fringe spacing, equals lambda d over S. And we also know the production of the interference pattern using white light. We should be aware of the appearance of the diffraction pattern from a single slit using monochromatic and white light, and have a treatment of the variation of the width of the central diffraction maxima with wavelength and slit width. We should be aware of the plane transmission grating at a normal instance with the derivation of d sine theta equals m lambda with applications of diffraction grating. We should recall that the refractive index of a substance is n equals c over cs. Recall that the refractive index of air is approximately 1 and that Snell's law for refraction at the boundary is n1 sine theta 1 equals n2 sine theta 2. We should know that with total internal reflection, sine critical angle is equal to n2 over n1, and have a simple treatment of fibre optics, including the function of the cladding, that understand optical fibres for step index, knowing that we can get material and modal dispersion, and you're expected to understand the principles and consequences of pulse broadening and absorption. So that brings an end to our revision session on refraction, diffraction and interference, which is part of the waves topic in AQA A-level physics. So thank you very much for listening, and as always, have a lovely day.